All right, let's just jump right into this. Welcome to another explainer where today we are unpacking something truly massive. We're going to be looking at the totally interconnected, rapidly escalating universe of Elon Musk's master plan. We are talking about a journey that goes from earthly supply chains all the way out to orbital mechanics and ultimately human evolution. The sheer scale of what is being planned here is absolutely mind-bending.
So I want to pose this question right off the bat. What on earth connects a $25 billion chip factory, a rocket, and your brain? I know, it sounds like a weird riddle, but as you'll see today, it's actually a highly calculated sequential roadmap for the next 50 years of human civilization.
To make sense of it all, we're going to follow this roadmap step by step. We'll start with Terafab and the reality of chip manufacturing, look at the impending AI power crisis, and explore why data centers might literally move to space. Then we'll break down the crazy thermal and radiation challenges up there, the risks of Kessler syndrome, and finally, what Neuralink means for humanity's actual future.
Let's start right here on the ground, with Terafab and chip manufacturing.
You know, right now, AI is experiencing explosive growth, and it demands immense volumes of high-tech GPUs. But the current chip supply chain, it's completely fragmented. We're dealing with extreme geographical bottlenecks. You've got photolithography happening in one country, silicon fabrication in another place like Taiwan, and then the final packaging is shipped all the way to Singapore. For an ecosystem that relies on autonomous neural nets, this fractured high-latency supply chain isn't just slow, it is a critical vulnerability. So Musk's proposed solution to this bottleneck is Terafab. The source material highlights this as a colossal investment. We're talking starting at $25 billion and potentially scaling all the way up to $110 billion. The goal here is to consolidate all those fragmented global steps under one single roof and increase global chip production by a staggering 50 times in a highly compressed time frame. This isn't just about selling chips to other people. It's absolutely crucial for vertically integrating his entire ecosystem. It ensures that Tesla, Grok, xAI, and those Optimus robots have the localized processing power they need without ever waiting on a disjointed global market.
Which brings us directly to the next major hurdle, the AI power crisis.
The sheer scale of the energy problem we are facing is staggering. As AI scales up, the sources predict that data centers could soon consume over 50% of Earth's electricity. Think about that. AI clusters require GPUs to run nonstop 24/7 for months on end. Not only does this heavily strain our local power grids, but it also consumes incredible amounts of water for cooling. It's actually to the point where some local communities near these centers are already experiencing low water pressure and noise pollution. The Earth's grid, as it stands right now, is fragile and simply cannot support this insatiable appetite.
So what do you do when Earth's grid is failing? You look to data centers in space. I know, this sounds like pure science fiction, but the math behind Musk's workaround is fascinating. The idea is to launch up to 1 million AI-equipped satellites into low Earth orbit. Why? Well, because in space, there are no clouds, there's no weather, and if you position them correctly, there's literally no night. You can harvest uninterrupted 24/7 solar energy. Originally, there were ideas floating around to beam this solar energy back down to Earth using microwaves, but the energy loss in that conversion is just way too high. So the new strategy? Bypass the planet entirely. Put the supercomputers, the actual data centers themselves, into space. They capture the solar power and process the AI data right there in orbit.
But of course, as any technical expert will tell you, we have to look at the radiation and thermal challenges of this plan. Putting a supercomputer into a vacuum is an engineering nightmare. The first major challenge is radiation. Down here on Earth, our atmosphere actually protects our computers. But out in space, cosmic rays and solar radiation can literally strike a microchip and cause what's known as a bit flip, which means it physically changes a 0 to a 1 in the system's code. That tiny flip can corrupt the data, crash the AI, or completely jeopardize the entire satellite. Overcoming this requires highly specialized, radiation-hardened chips, and those are incredibly difficult and expensive to manufacture at scale.
Then you have the second major challenge, thermal management. On Earth, cooling is fairly easy because convection handles the heat. A server gets hot, a fan blows air over it, and the heat dissipates into the room. But space is a vacuum. There is no air for convection, and while it's freezing cold in the shade, the side of a satellite facing the sun gets incredibly hot. So to cool a supercomputer in orbit, you are forced to use highly complex liquid cooling loops and massive thermal radiators that expel heat as infrared light, very similar to the incredibly expensive systems used on the International Space Station. Scaling that kind of plumbing to 1 million satellites, That is a monumental hurdle.
And the logistics don't stop there. We also have to talk about the Kessler syndrome threat.
Critics of this plan rightly point out the severe risks here, specifically Kessler syndrome. Imagine you have 1 million satellites in low Earth orbit. What happens if just one of them gets hit by a tiny asteroid or malfunctions and crashes into another? It triggers a massive chain reaction. Debris creates more debris, essentially forming an impenetrable shell of high-speed shrapnel around the planet. If this happens, it could trap humanity on Earth for decades or even centuries, making any future space travel completely impossible.
Furthermore, satellites don't last forever. When they reach the end of their lifespan and fall back to Earth, they burn up in the atmosphere. The source material notes some serious environmental pushback here. These dead, burning satellites release aluminum oxide, which actually poses a legitimate threat to Earth's ozone layer. Plus, under a 1967 UN treaty, nations are held responsible for the damage caused by their private companies in space. That means a major collision up there could spark some intense international conflict down here.
Okay, so let's escalate to the final stage of this vision, Neuralink and humanity's future.
To really understand Musk's goals for the next 50 years, we have to look at the Kardashev scale. If you aren't familiar, this is a framework used by astrophysicists to measure a civilization's technological advancement based on energy. A Type 1 civilization can harness all the energy available on its home planet. Right now, we aren't even close to there. We're roughly at 0.7. But this massive push to harness off-planet solar energy and automate physical labor, that is a direct attempt to rapidly accelerate humanity up this scale, pushing us toward Type 1 and eventually a Type 2 civilization.
So let's map out this speculative trajectory. Year 1 starts today, scaling Terafab to build those chips. Fast forward to year 10, and the goal is launching those orbital data centers to solve the power grid crisis. By year 20, as AI becomes vastly superior to humans, the focus shifts heavily to Neuralink to literally merge our brains with this technology. And finally, by year 50, leveraging all of this processing power and tech, the ultimate goal is achieving a multi-planetary civilization, likely starting with Mars. But why Neuralink? Well, currently, human biological memory and processing speeds are severely bottlenecked. Musk argues that as AI advances exponentially, humanity is going to become completely irrelevant unless we upgrade. The Neuralink future proposes this high-bandwidth integration with AI, basically giving humans superpower-like potential, virtually unlimited storage and processing power right in our heads. It's an attempt to stay competitive with the very machines we are building.
But what happens to everyday society in the meantime? If Optimus robots automate all physical labor, from agriculture to manufacturing, traditional jobs just disappear. The proposed economic solution for this is Universal Basic Income, or UBI, where the government or these mega corporations simply pay people to live. But the sources highlight a fascinating and maybe slightly terrifying prospect. We could see a massive divergence in the human species. Those who embrace Neuralink and AI might essentially become a cyborg species, while those who refuse could be left behind, creating unparalleled societal inequality.
And this leads us to a really profound philosophical dilemma. As the source material beautifully references, drawing parallels to thinkers like Nietzsche, if you remove work, struggle, and necessity from human life, you are left with a void of meaning. If AI is doing all our physical labor and computing our hardest problems, humanity is forced to entirely redefine its own purpose. Without the daily grind to survive, what do we actually do with our time?
We have seen how a single earthly chip factory leads to computers in space, which leads to brain implants and, eventually, a multi-planetary future. It is a wild, interconnected roadmap. So the final thought I'm going to leave you with today is this. As we stand on the absolute precipice of merging with machines to conquer the stars, is humanity, with all our current flaws and conflicts, truly ready for this transition? Thank you so much for joining me on this explainer. I'll see you in the next one.